Hello everyone, my name is Hasan Zerze. Today is December 9th, 2025. As I promised earlier, I would like to talk about why the energy is equal to mass, as Einstein found it first. So let me share screen. Okay, so I'm going to show why energy is equal to mass, and there are actually two steps involved in the derivation that I'm going to follow. First, we're going to show that when you go from one reference frame into another using the transformation TV, the energy is transformed as gamma V times the energy in the original reference frame, where gamma V is, as we talked about before, as we defined before, 1 over square root of 1 minus v square. Well, actually, there is divide, like it is more accurately, it is square root of 1 minus v square over c square. But if you work with units where the speed of light is equal to 1, then gamma v can be written as this. Okay, and with first we're going to show this, that we're going to show that this is true, and the second part of the proof is by assuming that this E prime is equal to gamma VE, we're going to show that the energy is identical to mass in units of speed of light being equal to 1. So more generally, we can write down E is equal to mc squared, but when we work with the units in which speed of light is 1, then E becomes equal to mass. So we're going to do the first part of the proof, okay, which is showing that the energy transforms as gamma V times the original energy. Okay, and we're going to make use of the Doppler effect that we had derived earlier in the previous videos. Suppose you have an object with a mass m, and suppose that it's radioactive and it radiates, and suppose we have two photons that's emanating away from this particle, and the photons have frequency nu, so the energy of each photon is h nu. So you have two photons that's going away from the particle because there's a radioactive decay of this particle and so on. So the energy change of this particle will be due to the loss of these photons. Since each photon has the energy h nu, we have 2h nu. So the energy of this particle will diminish by 2h nu, okay, in this frame of reference where the particle is stationary. And the reason why in our thought experiment we have two photons instead of one is I want to make it symmetrical so that we make sure that the particle is not pushed in one way or the other. So there is no velocity induced by the radiation. So that's why we use two photons, just to make it simpler so that we have symmetry, right? And suppose another observer in frame 2, like this is frame 1, right? And in frame 2, suppose this is the frame of a person who is moving in a vehicle that has a velocity v, okay? And from the perspective of the person in frame 2, the object with mass m will look as if it's radiating two photons with different frequencies, just because one of the photons will have a blue shift, the other one will have a red shift. The one on the right will have a red shifted photon, and the one on the left will be blue shifted. Okay, as we learned in the previous videos, due to Doppler effect, And we also have the expression when, you know, this transformation happens, TV. When we say TV, it's the transformation, Lorentz transformation, due to an observer moving at a velocity v with respect to the original reference frame. Okay, and we had found already that the redshifted photon will have a frequency nu divided by gamma v 1 plus v, and the energy of it will be just Planck's constant h times that. And the blue shifted photon will have a frequency of nu divided by gamma v 1 minus v this time, and multiplied by the Planck's constant, it gives us the energy of the photon. So according to frame 2, the observer in frame 2, the particle experiences an energy change of not 2h nu, but this time it experiences an energy difference delta E prime of equal to the sum of these two energies, which is 1 over, there's also this gamma v, I can factor out 1 minus v plus 1 over 1 plus v. Okay. And then with some algebra, we find that I need to make the common denominator, right? I have 1 plus v plus 1 minus v in the numerator, so I have 2 after simplification. Divided by 1 minus v squared is the multiplication of 1 minus v times 1 plus v. Okay, and from here we find 2h nu times 1 over gamma v 1 minus v squared. And if you write down the gamma v, which is 1 over square root of 1 minus v squared, right, as we defined earlier, this expression becomes, like this entire expression becomes 1 over square root of 1 minus v squared. So it's nothing but the gamma v itself. So 1 over gamma v 1 minus v squared is nothing but the gamma v itself. That's equal to 2h nu gamma v. Okay. In other words, if you compare the energy change of the particle with respect to two different reference frames, one has a multiplication factor of gamma v. So in order to transform the energy change, delta E, from frame 1 to frame 2, we multiply with the gamma v. Okay, so in short, what we found is delta E is transformed as delta E prime, which is equal to delta E itself, which is a 2h nu, this part, delta E, it was the original delta E, times a multiplication factor, gamma v. Okay, so this suggests that the energy that a particle has can be transformed using this multiplication factor. So we learned something very important. By going from one reference frame into another, the energy is transformed by multiplying with gamma v. That's the first thing that we wanted to show, right? So that's step number 1. So we showed this. Now we are going to use this fact to show that the energy is equal to mass. Okay. For this, we're going to make another thought experiment. We're going to have a frame 1 in which a particle with mass m is stationary, so it's not moving anywhere, so it doesn't have any kinetic energy, and the energy of this particle is nothing but the internal energy of this particle, right? Just the energy due to all the things that is inside of it, right? So there is no external energy that it has. Suppose it's not under the influence of any other field, any gravitational field, or if it's charged, any electromagnetic field, and so on. So it has an energy, an internal energy, U. Let me write it, internal energy. In frame 2, we have an observer that's moving in a vehicle that moves with a velocity v. So in his or her perspective, the particle with mass m will be seen as if it's moving to the left with a velocity v, correct? And the question is, what is going to be the energy of this particle with respect to this observer? And we're going to assume that we follow the Lorentz transformation, TV, because of the relative velocity of the frame 2 with respect to frame 1. And the energy with respect to the observer in frame 2 will be the internal energy of the particle plus 1/2 mv squared. Because now the object doesn't only have a mass m and stationary, but it also has some kinetic energy because it's moving to the left with a velocity v. Now, we're making a very important assumption here, which is not very obvious, but it is an assumption that we need to make. We're assuming that the internal energy of this particle is not changing, moving from one frame to the other, meaning that it has the same temperature. So we're assuming that the temperature of the object is not changing, or anything that relates to its internal energy of this particle, that's not changing. So we're just saying that, okay, this is the same particle. Say it is steel, 1 kilogram steel, at 20 degrees Celsius. It's regarded the same steel in the other reference frame. It's, again, 1 kilogram. Or you can think of it like that. You can say, okay, let me assume the particle has some internal energy, and that is related to just the rest frame of the particle, which is the frame 1. So I call this internal energy U at the rest frame. And then when I calculate the energy in the frame 2, I added the kinetic energy to that energy. Okay, so that there's a significant assumption here which could intuitively be assumed to be true. Okay. And this is equal to the energy, this is the AE prime, correct? We found that the energy observed by frame 2 must be the gamma V times the original energy in frame 1, which was U itself. So we have an equation, U plus 1/2 mv squared equals to gamma V U. Let's see what this is going to tell us. Now, if I solve for U, I will find out that U equals to 1/2 mv squared times 1 over gamma V minus 1. Okay. Now, at this point, you can actually Taylor expand this term 1 over gamma V minus 1, and you will realize that it is approximately equal to 1 over V squared over 2. So gamma V minus 1, or gamma V, is approximately equal to 1 plus V squared over 2 plus higher order terms. But we are assuming that we are working with small velocities, so the higher order terms are negligible. So this should be approximately true, correct? And then from here we find out that U is equal to 1/2 mv squared 2 over v squared. And after the cancellations, simplifications, we find out that the internal energy of an object is equal to the mass of the object. So we found out that the rest energy of the particle, which we can show as E, equals to m. And note that this is with the units where the speed of light is 1. If the speed of light is not 1 in a certain unit system, you can just write it as E equals to mc squared. Okay. But when c is taken 1, which was true for our derivation, you will find E is equal to m. But if you correct the units for any arbitrary unit system, you will get E equals to mc squared. So this ends our derivation. So we have shown that the rest energy of a particle or an object with rest mass m is equal to mc squared. Thank you very much for watching me. If you like this video, please click the like button and don't forget to subscribe to my channel.